Hello, my name is Nathaniel Acosta, and I am presenting Lab 1 on constant velocity. This is the introduction. For the purpose of this lab, we are going to demonstrate the difference between equilibrium in simulations and reality by observing an object with constant velocity in both. To model this, we use glow script simulation, track analysis, and graphs. Physics principles that I applied to this were Newton's first law, Newton's second law, and the kinematic equation. A quick preview of the results is that although at an equilibrium an object will continue moving forward at a constant speed in a simulation, in reality this is not so because of other forces such as friction and air resistance. Some quick assumptions we can make about this system is that the ball will be at constant velocity, and thus, due to Newton's first and second laws, because the ball is at constant velocity, it will remain at constant velocity unless there are outside forces acting on the ball. Furthermore, the normal force from the table counteracts the force of gravity, which means that the y component of the ball will stay the same. And the system is the ping pong ball, and the surroundings are the air in the table. This is the original video that will later be put into Tracker. The ping pong ball was rolled forward with a single push with no force applied after, and the positive x direction is to the left and the positive y direction is up. This is the Tracker video. The ping pong ball was measured per frame to be able to track the time and the distance of the ball, and the distance was measured using this little coordinate stick right here based off the yardstick in the background. These are the calculations for the simulation. Because it is a situation in equilibrium, we know that the net force is going to be 0. And because we can assume that the density of the ball is equally spread, which means that the center of the mass is at the exact center of the ball. The initial position will be set at 0, 0, and 0. And the initial velocity will just be the change in r over the change in time. I chose the initial time closest to the start of the tracker because, as we'll learn later, in reality, the ball will actually slow down because of outside forces. So this gives us a velocity of 1.0589, which we then set as our initial velocity. Because the ball will have constant velocity in our simulation, we set the initial and the final velocity to the same thing, and using this we can calculate through the simulation the final position, and it ends up at about 1.5 meters after about 1.5 seconds. Calculations for the tracker are a bit different because most of it is already given it to us through the video. Once again, we can assume that the F net is going to be 0. The density of the ball is going to be equally spread, which means that the center mass is at the center of the ball again, and the initial position will be 0, 0, and 0. However, the initial position will instead, or the initial velocity will instead be the delta r over delta t, which is the same formula, but over the entire period. This gives us a velocity of 0.589 meters per second, which, as you can see, is already much less than the initial simulation one. However, we can still assume that the final velocity and initial velocity are the same due to the constant velocity, and we use the kinematic formula to solve for the final position, and this assures us that the final position is going to be 1.06 meters per meters. Now we can compare the observed versus prediction comparison. On the table here on the right, you'll see the comparison between the observed motion curve and the predicted motion curve. The x-axis is the time and the y-axis is the distance, and as you can see, the observed motion fell much shorter than the predicted motion curve. And the main issue for this, or the main reason why, is because of forces of friction and air resistance and some irregularities on the table or around the ball that could cause the ball to slow down in reality, but because we decided to not calculate any of that in the simulation and only use the initial velocity, the ball will not slow down in the simulation, as can be shown by this straight slope versus the slightly curved slope of the observed motion. So the overall conclusion is that the friction force and air resistance acting on the ball in reality caused it to travel less distance than expected by the prediction motion simulation. However, with a smoother table or in a vacuum, this difference would not be as noticeable, but would still need to be accounted for problems that required to no error. This experiment was quite useful for building some intuition behind what we do in class in terms of the problems and why we may ignore friction, because things can start to get very complicated, as shown by these possible errors. For instance, there could be a difference between the center mass on the ball as marked in Tracker and the actual center mass due to the inaccuracy that comes with doing it by hand, and irregularities on the ball such as bumps or dimples, and the table such as eraser shavings may have altered the trajectory and the velocity of the ball in Tracker. Now what if the axes were flipped? If the axes were flipped, then the RF vi, and vf variables would all become negative instead of positive. However, the magnitude of each would remain the same. What does this difference mean? The difference between the observational experiment and the simulation can be described as caused by external forces not considered by the simulation. However, the simulation could also be changed to account for these forces such as friction and air resistance. Thank you for your time, and have a great one.